Stokes theorem part three. Just to recall, we looked at this interesting example where we had a cube, a bottomless cube with this boundary. We evaluated the path integral around the boundary. We got -2. And now we're going to evaluate the flux of the curl through the top, the region, the solid that this bounded. So we're going to do the front face, the right face, the back face, the left face, and the top face, and it should tally up to 2. So first of all, we need to figure out the curl. Del cross F, which is a curl. I put the partial operators here. This is the vector field, y, -x, x. Copy 2 columns over. And if you do the crisscross thing, you'll see that one's 0, that one's 0, z partial of y. That one's -1, x partial on -x is -1k. When you go this way, we have y partial of y is 1, but it's negative. Okay, and then we have z partial of -x 0, x partial of x is 1, so we make that -j, so we get -j minus 2k. That is what the curl is. There can be variables in here, by the way. In this case, the curl's constant. I kept it toned down, but there could be x's and y's in here, and of course these integrations can become much more complicated. But I'm happy with you just to figure out what these various symbols mean. So we're going to start with the front. On the front, we have a normal vector as I. It's parallel to the x-axis. That's this vector right here. And so when we do curl dot n, we do our curl vector dot I. Okay, that gives you 0. We have a 0i here times 1 is 0. So we're going to integrate 0. One important note, you're integrating on this face. It's really a yz double integral. X is equal to 1, but we don't really need that. If we needed, if this for instance was a function of x, then we may have to plug in x equals 1. But the point is, y and z go from 0 to 1. Y goes 0 to 1, z goes 0 to 1. It integrates over the square. Integrate 0, we get 0. So we put 0 up in our tally here. Now let's erase this and do the right side. In that case, our normal vector is j. It goes along the y-axis. And so del cross F dot n equals -j minus 2k dotted on j, and you get -1. -1 times +1 is -1. All the other 3 components are 0. And so we're going to integrate -1. Now, this here is really an xz integral. So you can do dx dz 0 to 1, 0 to 1. Well, that's just going to be a unit square. Times -1, we get -1. So I'm going to put -1 over in my tally. And then we'll do the back. You can guess what the back is going to be. Okay, now, somewhat important, the normal actually goes backwards, so it's an outward normal, and it goes in the -x direction. So it's -I. Okay, so we want to dot the curl, -j minus 2k, dotted on -I is 0, and so you can integrate 0 dy dz, and you get 0. And so we're going to put 0 in our tally there. And then we'll do the left side. And in this case, the normal vector, it's negative j, it's pointing back here. Del cross f dot n is negative j minus 2k dot negative j. Now that happens to be positive 1. And so we're going to do a double integral, 0 to 1, 0 to 1, positive 1. And that's a dx dz integral. That would only be important, by the way, if this ended up being a function of x, y, and z, for instance. So you can put any letters in here to get the right answer. So you got 1. Okay, well, we're back to 0. Okay, you can probably guess what's going to happen on top here. Okay, on the top, okay, the normal vector equals k, and del cross f dot n is equal to negative j minus 2k dotted on k equals negative 2. Okay, it looks like the top saved the day. And so we're going to integrate negative 2 dy dx, or dx dy, doesn't really matter. We're integrating over this top surface. It's an xy integral. And so we get negative 2. Add this all up, you get negative 2. And so the double integral, this is what's called a surface integral, by the way. It's called a surface integral, also called a flux integral. You're really calculating the flux of the curl, and that's a type of a surface integral. This is equal to 0 minus 1 plus 0 plus 1 minus 2. And the grand total is minus 2. And so we verified it. This is not a proof, but it's a verification. So there are interesting ways to prove Stoke's theorem. The proof isn't that difficult. We're not going to go into it. But in Calculus 3, at a good university, we're usually happy if you can figure out what these symbols mean. And then if you see this in another text used conceptually, whether it's in electricity and magnetism or advanced physics class, or then you'll at least be able to read and comprehend what it is they're talking about. So, that's it for Stoke's theorem.